Welcome back to electric fields. Now, this unit or this video, it's kind of like a little bonus, but a very helpful bonus to help think about things. So previously we have looked at how to draw field lines, those fancy, nice pictures, squares and straight lines and all kinds of stuff. We can also look at how to calculate E field strength, called the E. Well, define field strength and calculate E field strength. Didn't see that there. And then, of course, calculate the force that depends on the field strength or also the plate separation and the potential difference between two plates. That's particularly for uniform electric fields only. Now, one little one I've added is the green one. How do you find work done on a charge in electric field? This video will link certain ideas from previous chapters, like chapter 6, like chapter 5, also forces. So we're going to use those basic ideas, apply it to electric field so it helps you expand your understanding of work done, energy, and forces. So let's take a look. What is the work done and how do you think of it in electric fields? Firstly, this is an old question that we have looked at before. It's from a chapter 5 handout a very long time ago. But here, it said, okay, you have a negative electric charge in a uniform electric field, and then a mass in a uniform gravitational field. Which one shows the direction of forces? Okay, so they gave us some choices here. Now I want you to notice some parallel language here. Same language lah. So in the electric field, you have a charge sitting there, and then the charge will move around. For gravitational field, you have a mass there, and then the mass will move around. Notice how both are fields. When you have something in the field, that something experiences a force. In the electric case, it will be electric force. In the gravitational field, it will be a gravitational force, mg. So let's look at the old one that we're familiar with, gravitational fields. You see the arrow pointing to the right? All these arrows? That is pointing to where? Pointing to the center of the Earth. So actually the Earth is curved lah, but if you draw kind of a straight line, here is the center of the Earth. If you zoom in on a small enough area, it will look almost straight and you have a uniform gravitational field. So if you have some mass sitting there, it will experience what? Well, here is at a pretty high potential. See, potential is like GH, but it has some potential energy, so that's what I'm familiar with, like MGH. Okay, GH is like kind of like the potential of it. So it will experience a force that will bring it down to a lower potential. Okay, this one is like tilted sideways, but you imagine you're holding a ball. When you let go, it will want to go down. So in this case, they kind of rotated the whole thing a bit. So down is to the right. So it will experience a gravitational force, Fg, or what you know as weight, W, towards the floor, which is currently vertical. So that's the first one. On the right side, you see, okay, this one confirmed wrong because wrong direction. Now you want to go to the center of the Earth, huh? Then how about the electric field? We say that the arrows in the electric field is where a positive charge would go. Positive charge will go in the direction of these arrows, which is why we define the arrows lah. Just like how if you have a mass, the mass will go this way. That's why we draw just why we draw gravitational field lines this way. Okay, but this electric field convention is for positive charge. So positive charge will move to the right, but a negative charge will be opposite of that. So a negative charge will actually go this. Oops, where is my pen? There we go. This way. That's where a negative charge would go. And that is what we call the electric force, which is proportional to what charge that is and what E. Okay, so you can think of it this way. Previously, we say, okay, the force, which is the weight, is mg. M depends on the stuff that is in there. Like, is it a ball? Is it a table? Is it a book? What are you dropping? How heavy is it? That's a property of the object itself. In electric fields, you also have electric force. I'll put this here, Fg. But we know it is, well, something else called QE. Q here is the property of the charge itself. How many coulombs is it? Is it lots of coulombs, small coulomb? What is the charge, the thing that you're putting in the field? Then of course we have E, which is a property of the field strength. Let me say here, property of field, or I can say the field strength. That is very similar to the G here. This G that we know as 9.81 is a property of the gravitational field on Earth and the surface of the Earth. If you're on another planet, your G is different already. Okay? So these are the parallels between the fields. It's actually almost the same thing. Just a little bit difference between these two fields and stuff like that. Okay? So it's good to start thinking about this. Now, one last thing I want to point out to you is potential. We talk about potential difference, right? Here got if you are high up and then you drop, then you go lower. There's a potential difference. Difference in potential energy, MGH, MGH. We have the same thing in electric fields. How do we think of that? How do we think of potential? Well, here's how we can think of it. Let's look at the next slide. So previously we looked at a picture like this. Remember, I drew the electric field. I said, okay, let's make this left side kind of a higher potential, what we call the positive side. The right side, let's make it a lower potential, or sometimes you call it negative side. So here is higher potential, lower potential, because we connect it to a circuit now. Okay, connect. Okay, that's from the previous picture. And then previously we say that the potential difference of the circuit is 1000 volt, or connect to the power circuit, 1000. Means the potential difference will be from 1000 to on one side, all the way down to 0 on the other side. Okay, then of course we have our electric field lines that point from positive to negative, or in this case you think of it as pointing from a higher potential to the lower potential side. So that's where we have the arrow, 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 arrow. Okay, that's what we're looking at. Now, hopefully, quick quiz. If I put a positive charge, where would it go? You would say, oh, away from the positive towards the negative, yes. But what if we didn't have this positive negative? Then you would think of it, oh, follow the direction of the arrow, or you can say from a higher potential to lower potential. That's what a positive charge or positive object would do. So if we want to plot, let's say, a graph of potential difference against distance from, let's say, the left side, how would that look like? Okay. First things first. You see how we have one plate 100 and the other plate is 0 volts, right? That is, at one side, if I say this side is my reference point, then here I will have 100 volts. Then on the other end, I'm going to have 0 volts. So at this point, I'll have some separation D all the way, the whole D. And at that point, I will have 0 volts, so I should put a point there. There we go. But what happens in between? Let's see. So if 100 is on one side, 0 is on the other, then in between is what? Should be 50 volts. And then, too many lines. So let's say we have here 50 volts. Then half of the half here should be halfway, which is about 75 volts. And the last one, halfway, will be between 0 and 50, so 25 volts. These lines are what we call equipotential lines. What does equipotential mean? Equi, kind of like equal. Equi, kind of like an equal potential line. So along this whole line, everywhere in the electric field, the potential is 25 volts. Now, before I go a little further, you're like, what is potential again means? Okay, think of it this way. You are on a mountain. Okay, you on a mountain. At different places, you have different heights, right? If I say the reference point, if I say here is 0 meters, then I say maybe halfway is 50 meters. Then I say, oh, maybe on the top here is 100 meters. These are also what we call equipotential lines, kind of in a way, because it's based on height. Okay, so then I can continue to divide and say, oh, if here's 75 meters. So anywhere you are, if you are here inside the mountain or outside the mountain or here, you will have the same potential energy. If you're here or here, the same potential energy. Okay, so that's why it means like kind of like equipotential. Think of heights, if that's more familiar with you. You're going from higher to lower potential. It's like a hill, you're rolling down the hill. So if I put a ball here, what's going to happen to the ball? It's going to roll downhill because it wants to go to lower potential. It's like, I stay up here very uncomfortable, I want to go lower potential. So all kinds, that is why stuff will go to lower potential and experience a force. Go lower potential. Okay. So here, all right, if I plot all my points, halfway through I get 50. Here is like d over 2, so halfway, so I should get this point. And if I plot everything, I should get a nice, well, let's redraw that as a blue color so it looks nicer. I should get a nice straight line, and that is the relationship between potential difference, not the whole plate's potential difference, potential difference between from the reference plate on the left side to some distance. So maybe here to here we'll have some potential difference. And that is, what is the potential difference? That will give me a 25 change. So that's how you can think of equipotentials and potential lines. Some final notes I want you to know is that there is one funny convention. Normally we say, right, E is V over D. That's how we know the electric field strength. But here actually, based on this graph, the true way to write it is actually E, let me rub this off, E actually equal to gradient of the graph, of the VD graph here. Because you want to find gradient of this graph is V divided by D ma. Okay, so V divided by D is electric field. But notice this gradient is the other way. So actually it's negative gradient of graph. Positive gradient is going up like that. Okay, so actually the real way to write it, the proper way to write it based on diagrams and things like that is energy. Electric field strength is actually negative change in voltage over change in distance from the one plate or distance between 2 points. This is basically like what you do in lab usually to find gradient. You say change in y over change in x gradient. Similarly, this is how the true way to write it. Okay, usually we don't care about the negative when we're solving problems. That's okay. And last thing, there's another name for this thing. We call this also the potential gradient. Just like how you are rolling down a hill if you are on a mountain top, if we put a nice cute little positive charge here, it will also roll down the hill. Roll down the hill, which basically means moving to the right. But be careful of negative charges because they are acting opposite. So if you put a negative charge on the potential hill, it will actually roll up the hill. Because if you put a negative charge here, it's gonna go this way. Okay, so that's just what I mean. Think of it as hills. Higher potential means wow, very high on the hill. Low potential means very low. So where would it go? Well, like masses, positive test charge will go downhill. Electrons, negative charges are the reverse of that. So these are the parallels of these two things. Let's look at a very quick simulation in fact, that how you can use it to play with equipotential lines better and see how they change. Okay, so here is GeoGebra again, but this time we're going to use this equipotential line function. Previously we looked at how the electric field is the same everywhere in a uniform electric field. But let's reset this a little bit. Okay, there we go. So now, if I want to look at equipotential lines only, I can select these stuff and I can see, okay, if I have one plate at 0 volts and another plate at 100 volts, means up here is like the top of the mountain. Think of this as a slope that is kind of like 2D space like this, and then you can roll positive charges down the slope. Which means if I have, let's say pretend this think it's a positive charge. I put a positive charge here, it's going to roll down the slope. Roll down the gradient line, if you want to say it that way. Okay, it's going to roll down, let's say from 60 volts. Pretty high potential, so it's going to go down to lower potential. But if I use a negative charge, the negative charge wants to go up the potential. Remember, negative charge are kind of weird. They're just rebels. They're like, okay, YOLO, I'm gonna oppose everyone and do the opposite of what everyone's doing. Okay, sure, do what you do. That's the negative charge. But yes, play around with this thing. Notice how if you change plate separation, it doesn't really affect the potential difference between the two plates. Okay, it's still 0 to 100. But what changes is, wow, the slope becomes steeper. Because over a short distance, you have to drop by 100 volts. Okay, if I draw in like a side view like this, kind of like using the slope analogy, if you have to drop 100 volts in pretty long distance, it's kind of like that. If you have to drop 100 volts in a very short distance, wow, that's a very, very big, steep slope that will roll stuff either down or up. And that also means that if the slope is very gentle, remember slope is electric field, this one is called a low electric field strength. Whereas if it's very, very steep, the potential gradient is so steep, that's also what we call a very, very strong electric field strength. Now notice also, what if I play with something else called a voltage here? Now I'm giving both plates a supply of 100 volts, okay? So 100 law, 0 to 100. But if I decrease it a little bit, let's say to 20. So it means the bottom here is 0, up here is 20. So that's kind of like, well, you're still rolling downhill, but the top of the hill is not very high. It's only at 20 volts. So lower potential. So positive charges will experience a smaller force because the electric field strength is not as strong. Okay, so play around with these things. Learn two different ways to think about where charges go. Firstly, think about, oh, if positive charge, it will attract here and repel there. That's one way to think about it. But if they don't give you positive, negative, you also want to be able to think of potentials. From 20 to 0 volts, where would a positive charge go? Would it go downhill towards 0 volts or uphill towards a higher potential of 20 volts? That's all for this short simulation. We'll play around with it. The link is in the description below. Now, all that potential stuff was to prepare you to think about work done in fields. Okay, good old work done from chapter 6. Hopefully you still remember. Oh, if you are wondering, like, Miss, will we have questions about potential stuff? Kind of blur on that. Well, at AS, they will not ask you so much about potential gradients and equipotential lines. That is more of an A2 topic. But it's kind of the fundamental idea you must know in order to think about work done. Or make work done have more sense lah. It's not just a formula memorized, like, oh, you're sliding downhill, kind of like in gravitational fields. Okay? So work done in fields. Let's look at the parallels. Previously, in chapter 6, we say work done is force times displacement. Or force times distance, however you want to memorize it, in the direction of the force. And we look at a diagram like this in chapter 6. You have a gravitational field like this. Gravitational field. And then if you have a box up there weighing, let's say, 2 kg, or M, M for mass, then that box, once you let go, will go down and then hit the floor. And that's because up here is at a higher potential, and it has a potential to do work. So what the field is going to do is it's going to pull that box down to a lower potential. So the Earth's gravitational field did some work on the box. Okay? But the box itself lost potential energy because it's going from high place to all the way down there. Very similarly, we also have electric fields. I use pink color to, so you don't confuse that. Pink color is like color of lightning, so related to electricity, and it's going to thunderstorm again. I hear thunder. Hopefully you don't hear it. It's too rumbly. Let's say you have a charge, a positive one. Ding. It is going to experience an electric force, very similar to this gravitational force. Okay, this fellow experiences electric force, same direction as the electric field, and then the charge will, if you let go of the charge, it will go beep, and then you'll touch the lower potential area. Or you could call it the negative plate, some people call it the ground plate. But also, same thing, it's kind of at a higher potential. And you want to go to a lower potential. That's why you experience a force and you go down, and there's also a work done because there's a change in potential energy here. Okay, so let's say I say here is 0 volts, like up there is, I don't know, 200 volts, something like that. But you need to be careful. There are rebels in electricity called electrons or negative charges. If you have a negative charge somewhere in the middle, it actually experiences a force up in opposite direction. And it's going to go against the arrows of the electric field line. So it's going to go zip upwards. Wow, rebel, huh? But it's still at the higher potential up here. Maybe 200 volts or so. Higher potential. And here is lower potential. Kind of like 0 volts or so. Okay, so these are the differences between the different fields. But the principle of calculating work done is the same. So we're going to visit some old stuff a bit. Good revision also. Work is what we call force times displacement. S is distance. So previously we say S is from, let's say, here to here. That is S. That's how far the thing traveled. You can do the same thing for our charges as well. How far did it travel in the electric field? Or in other words, we'll use something a little bit more familiar. Work is force times a distance traveled in the electric field. So if I say, let me take the bottom of the charge and then travel to here. What is this distance? Oh, change in distance, okay? Change in distance. So this D here is not plate separation, it's where the charge move distance. D. Okay? So now we have something moving, we have F. What do we do next? How do we expand this idea of work done to make it specific for electric field? Well, let's try sub in something about force, Fe, in this case. So if we plug in, what is force again? The force acting on these small particles is Q times E. All right, the charge of the particle times the electric field strength. Okay, so let's plug it in. F equals to QE. And then times D. That's it. Okay, so that's one form of the equation we can use to calculate the work done. W here means work done. Also meaning change in energy of that particle. But there's one more step we can use to specialize this formula for electricity. Can you think of any other equation we can sub into here? There's one more equation specially for uniform electric fields, and that is electric field strength of a uniform electric field is the potential difference, I should say, divided by distance, or more accurately, we should say the change in potential over change in distance. For this change in distance, this distance, what is the difference in potential? That's a better way to think about it. So by right, I should say change in V over change in D. So let's try sub that in. So if I sub that in, let me see, ED, what is ED? E times D is, well, let me regroup it for you to see. ED is actually Q times change in V. So change in potential if you go from top to bottom. So this one is the specialized work done formula for charges in electric fields. Yay! So if you start at, let's say, 200 volts, and then you end up at the bottom, which is, I don't know, maybe 100 volts, then the change in potential difference is only 100 volts. This is your change in potential difference. Okay, so that's what it means, change in potential difference and what charge. So we're going to look at some examples of how to calculate work done in charges. Make sure you put in your brains to it, pause it, think about it, because this will be a very, very helpful expansion of your understanding of work done and changes in energy. First on the list is this round looking question. Okay, before you do this question, I'm gonna give you a heads up. CIA somehow loves this question. Probably a ton of students get it wrong, so it has appeared more than once in past year, like exact same question. This is on page 7, by the way, if you have the handout and you want to try along with it. Yeah, there are a few that looks like this, but I'm looking at the one on page 7. So what's happening here? You have 2 points 90 degrees apart on a circle. A positive point charge is right at the center of the circle and creates an electric field of magnitude E. Okay, so that means if I use light blue, I guess I could use light blue. There's a positive charge in the middle and it has an electric field, which looks something like this. Yeah, something like that. Imagine they're all straight and it's positive, so all lines out and away from the center. And it says this field creates electric field strength, which is the same at P and it's the same at Q, same field strength. Which expression gives the work done when you move the poor little charge from P all the way down to Q? What is the work done? This one, you must pause this video and try it out. It's a very short one relatively, so grab a piece of paper, try it out, then only we'll know if we really will get it wrong or right. Okay, then you'll know like, oh, this is a misconception that I have. I should probably fix that. Okay, so pause it, try it out, and we'll go through it together. All right, let's see. Now, remember I mentioned about equipotential lines just now. Okay, so what's happening here is same field strength here, same field strength here, and well, as you go on along, this circle is actually what we call an equipotential line. You're like, Miss, we didn't really talk about equipotential line in circles. Well, I'm just telling you, you can have equipotential line on circles. Because this is a non-uniform electric field, which means down here in this circle, you have the same electric field strength everywhere. And you can say also same potential. And then you have another electric field strength here, which is different from the first one, and another one, and then you finally get to that part. But here you will want to find the work done as you move from P to Q. So let's highlight out this area as you move from here to here. Now the thing is, work done depends on what your charge is times the change in potential. But is there a change in potential? Well, the trick here is there is no change in potential, and therefore there is no work done. Dun, dun, dun. Because here is the same potential, so all along this circle is the same. Now, if you how this is different from the parallel plates that we've been looking at. Parallel plates, if you have fields like this, then your potential lines are straight like that. But if you kind of curve these potential lines a little bit, because they're coming from a round source, then your equipotential lines will also curve and become something like this. Okay, you see how the curving happens? Okay, they're all straight. Equipotential lines are straight. So yeah, you can extend this to circular charges, and then all the same potential lines are here. Which means if you have, I don't know, create a number 10 volts here, you have 10 volts here, you have 10 volts here, 10 volts here. So no change in potential. So it should be 0. So make sure you got this right also. Throw back to gravitational force. Okay. If you move from this part of the planet to another part of the planet with the same height, no change in gravitational potential energy. Okay. Remember, work done is change in mgh. But if there is no change in height, there is no work done. If you're just moving from the same potential to a same potential. Okay, you should get this one right. Make notes, draw little warning signs on your paper as well. This other question, something a little bit to do with calculations. This one's on page 4, past year, if you have the handout. Let's take a look at what they're asking us to calculate here. So you have a positive charge in the electric field, okay, with that field strength. How much work must be done to move it a distance in the opposite direction of the electric field? Wow. Okay, if you just read that and kind of feel confused, first thing to do is pause the video and draw a picture. You must try to interpret the information, because if you can't interpret, you can't solve. That's a lot of what people have when they try to solve calculation questions, like, Miss, I don't know how to start. I said, have you drawn a question? No? Okay, go draw it first. Draw it, suddenly it becomes clear, because then you see what's happening. So try to interpret it. Then resume the video, and I'll draw a picture as well, and we can take a look how to solve this thing. So hopefully you got to kind of figure out what is happening here. You can draw a field strength pointing in any direction, but I like stuff going to the right, so I'm going to draw field lines going to the right. You can draw it going down, going to the left. It's okay, don't erase your picture. So I'm going to say, okay, let's say there's field lines pointing here. And you got a little tiny little charge there. Okay, some charge. A positive charge, what more? Okay, so positive charge. And it's in a constant field strength of 300, well, how many? 300,000 volts per, that's very high electric field. How much work must be done to move it 4 millimeters in the opposite direction of the field? Means I have a positive charge there. I'm going to use my hand or my whatever I'm going to do. I'm going to try and move it opposite direction. So I'm going to try and move it here. Put dotted to mean like I want to move there. There we go. Now notice how that's against what the charge would normally do. Right? The field lines say that the charge normally would want to just go there, but I'm pushing it against its wheel, pushing it to the left a little bit. Okay? So how much work should be done? Well, I kind of scratched your head a little bit. Well, we know work done is Q times change in potential. But we don't have any of that information. All we know is we move this fella by 4 millimeters. Move there. That's it. But how do we know the change in potential? When you move it from here to here, you're changing the equipotential line. So what is the change in potential here? We need to find that. How will we find it? Any ideas? There's one piece of information we haven't used yet, and that is the electric field strength of 300,000. How to use? Well, remember the definition of electric field strength? Recall. Electric field strength means you have a certain change in potential over a change in distance. Oh, so we could use the E in here to find a change in potential difference. Means in the electric field strength, if I move 4 millimeters, I can calculate what change in potential that is by rearranging to be like this. So I plug in my E and the change in distance. Nice. So actually, I'm going to shortcut a bit and plug everything in one line over here. So change in V we know is E times change in distance. Okay, how far is this change in distance? And things like that. No change in E, sorry. Change in V and change in D. Now let's plug in everything we know. Positive charge. Okay, so 2.6, 10 to the negative 8. Electric field strength, 300,000 volts per meter. So I need to convert everything. I should write down my units to make sure we're all on the same units. Make sure your charge is in coulomb. Electric field strength is volts per meter. And lastly, change in distance. Oh, we're in meters. Oh, we need to change 4 millimeters to meters. Okay, make sure I don't error this one. Meters. So this is 4 millimeters. That's why 10 to the negative 3. Now we can calculate and see. 2.6 times 10 negative 8 times 300,000. 4 times 10 negative 3. Ooh, what an interesting number. So here the number you get is the work done, aka change in energy, when you move that charge to another position, will be 3.12 times 10 to the negative 5. That corresponds to which answer again? Oh, they only do 2 SF. Okay lah. So that corresponds to 3.1 times 10 to the negative 5. What's the unit of change in energy? Energy? Joules. Joules. If you ever forget joules, just name your future child Joel or something like that, middle name Joel, then you will for real remember it for life. So here we have 3.1, which is the answer to this work done in changing that. Now, as a side fun fact, what if I move this charge instead of moving to that position which I just drew? What if I moved it here? Will there be any change in energy? Will there be any work done? No, no, no. If I just move it horizontally, you're at the same equipotential field line, so no work done if I did this. No work done if I moved it here. Move here, the other one, got work done. Just remember, if you're confused again, parallel to the Earth that has a field, and if you move an object up or down, only got change in height, only got work done. Similar here, if you move it up or down, then only got work done because there's a change in potential. In this case, potential difference is the volts lah. Okay, so this is the calculation question. Let's go to something a little bit more applied. How do we apply these ideas of work done? Finding field strength. Ooh. Now we have strange numbers, no more straightforward calculations. These are what I call algebraic questions, where they give you equation or they ask you for equation. This is on page 8, a little bit over. Now try this one out. Try to use this knowledge of work done that you have sharpened a little bit to see what is the electric field strength between the plates. Okay, let's take a look at this question together. A charge move. Ew, negative, be very careful. This is a negative charge, means it's going to be a rebel. Okay, anyway, that's a fun fact. Moves from rest, that's important. Okay, from rest means your initial velocity is 0. From plate X all the way to plate Y. Okay, and it ends over there. When it reaches there, it finally has some other kinetic energy. Okay, interesting. Now, which expression gives the electric field strength between the plates? Well, let's see. Electric field strength. That's the E stuff. That's related to V over D, or change in V over D more accurately, which is also, what else can we calculate it with? F equals to QE, so E is F over Q. These are all the equations you want to write out straight away to see. But how do we find E? We know E is V over D, but do we know V? Do we know D? We don't really know all that stuff. But the hint is, it talks about kinetic energy. Why is there kinetic energy? Because over here, you start from rest, it's sleeping, no energy. Then somehow, it will experience a force. Zoop. And it speeds up and it ends up on the right side with some kinetic energy K. That's considered a change in energy, which is also called a work done. So some work has been done on this little particle to get it up to some kinetic energy. Now, if you're wondering what is this two line up here, it means battery lah. The long one is positive, so you consider this a positive plate and a negative plate. So yeah, the negative charge is moving towards the positive plate. So there is some work done. So let's talk about this. Work done, as we derived previously, is what? Q times change in velocity, change in potential. But we don't know the potential. Good. We are stuck. Are we stuck? Wait a second. Work done also means change in energy, right? Change in energy? So I can rewrite this whole thing as a change in energy, which is kinetic energy K minus or initial kinetic energy, which is just 0, equals to Q change in potential. Well, that's just K, because 0. But they want electric field strength. We need to get an E involved somehow. Well, let's bring in the other equation here. So what we're trying to do now is we're trying to manipulate equations to get the answer that they want. Okay, so we want electric field strength, right? Let's get E into the picture. So we know E is change in V over change in D. ooh, we can find change in V here. So let me just rearrange this. This is K over Q. Let's sub in that in here. So now V is K over Q time divided by D. Or D, if you define it as the distance it has moved, then that's just K over QD. Let's see which one matches the answer. That would be C in this case, K over QD. Ah, so that's how we can find it. Now notice, like, Miss, is there a fixed formula to do this kind of questions? Not really. You have to do alphabet gymnastics. Just write down all the equations you know about electricity and work down all the keywords, write everything out, and see how you can play with this formula, substitute here, substitute there, to get what they want. That's the best way you can approach algebraic equations like this. But then again, they tend to repeat questions like this. So if you practice more, you get a hang of what's happening here. Now, some of you may have used a slightly different method to solve this. Is there other ways? Yes, there's other ways. Well, let me just draw a line and just give other method, which is basically the same thing but in different form. Some of you will say, Miss, can I just use, like, oh, this one got electric force, so force times distance is work done. Can I do that? Can. Why not? I don't see why not. So work done is force times displacement, which is in this case is F times D. And work done is a change in energy. So then the next step is change in energy will be final kinetic minus initial, which is at rest. Then the electric force will be QE times how far it has traveled in this case. How far this force has acted on the particle, I should say, in better terms. So QED, which then says you can rearrange to get K over QD equals to E. Both works. It's the same thing. Okay, so different ways, all the same work done stuff, but now in algebraic terms with electric field stuff happening. This final question for this video is about the same thing, change in kinetic energy, work done, but with a little twist now at an angle. So I would say pause the video, try this one out as well, okay? And see if you can figure out how to get to the final answer for this one. There are lots of little tricks and traps on the way, so be very careful. It might take you some time, but that's okay. You can also brainstorm with a friend and try to solve it together. You know, just message a friend and say, hey, how to do? What's your ideas? Maybe you got it wrong. Maybe I got it right. I don't know. So let's see. Distance between x and y is 4 cm. Means this is 4 cm. So that you should ring a bell. Oh, that's the displacement. Okay. And a line xy is an angle 60 degree to the direction of the field. Ooh, that means this is 60 degree. Okay. The field exerts the only force on the electron, means don't consider other forces. The field strength is 100 Newton per Coulomb. Okay, so we know E is 100 NC. What is the change in kinetic energy as it moves from X to Y? Whoa there. Change in kinetic energy is kind of like change in energy, which is work done, which is the charge times the change in potential. How are we gonna find all that stuff with all these things? Okay, let's go through it very, very carefully, step by step. First things first, can we find a change in energy? That's what we're trying to find. So change in kinetic energy, let's rewrite this, is the work done, which is Q times change in potential. How do we find the potential? Remember. Electric field is change in potential over change in distance. So for that distance, what is the change in potential? And we want to use this in our main equation here on the left side. So let me just rearrange a little bit. Change in V is E times change in, D. So then we'll use a Q times E times change in D. Okay, so let's go step by step. Do we know Q? We don't know Q. How do we know what's the charge of this electron? Wait, did I just say electron? Hey, we do know the charge of electron. It's a standard formula we should memorize. Remember from previous one. What is the charge of an electron? You can find it on the back of a calculator or on inside the formula sheet for exams, or you can just memorize it. It's 1.6 times 10 to the negative 19 coulombs. This is the standard charge of an electron or proton, but electron lah. So with that in mind, let's plug in the values. 1.6 times 10 to the negative 19 coulomb. This one you must memorize or know where to find the value. Now the E part is given to us. It's 100 Newton per coulomb. Okay, no need to change unit there. Now the D part, we have to scratch our heads a little bit. What is the distance here? What distance should we use? Should I use 4 cm? Should I use something else? Now this D here, we want to look at the change here, which is related to the change in potential. So this change in potential and this change in distance should be parallel to each other. So remember we talked about potential lines, equipotential lines. If here is one line, here is one line, here is one line, one line, one line, one line, all the way until, I don't know, maybe this one is 0 volts, is like maybe 100 or some value lah. So we actually want to find the D, the distance, is the one that's like that, because we want to say, oh, for this change in potential, what is this change in distance? D. Wow, it's getting real crowded there. Let me redraw this thing. X, Y, and of course this thing. We want to find the change in distance D here. So we don't use 4 cm. We want to use the change in distance, which is parallel to the electric field. Okay, because it follows the change in potential lines, which look like this. There's some change in potential happening here. Okay, so we need to do some trigo stuff. Fair. Okay, so we need to times, oh, no more space, I'm going to write the next line. This is, how do I find this? The adjacent hypotenuse. So you need to do 4 meters. This is in meters. Times cosine of 60. Wow. That is a lot to type in, but let's do it. Now let's plug it in. 1.6 times 10 negative 19. 100. 4 times 10 negative 2. Cosine of 60. All right. So what do we get? We get something really, really small. 3.2 times 10 to the negative 19 joules. And you panic and like, oh, that's none of the answers. What's happening here? That's none of the answers. That's very interesting. Don't panic. EV is actually another way of talking about joules. Joules is energy. EV is also energy. In fact, I would say, how do you convert between EV and joules? Well, you could say 1 EV is 1.6 times 10 to the negative 19 joules. Where did we see this before? This looks very familiar. That's the charge of an electron. Interesting. So this is the conversion you want to remember. So what you could do is, you divide this by E, which is 1.6 times 10 to the negative 19. That is joules per EV kind of thing. Okay, sure, let me do that. 1.6 times 10 to the negative 19 joules. That will give me 2 EV. Now what we have just did is we converted joules to EV. EV is another way of expressing energy. Okay, and also as a side note, if you did calculation for only this part, you will also get 2, because this part is the this 1.6 times 10 negative 19. This is the extra part that contributes the E. E is 1.6 times 10 to the negative 19 lah. And notice how if this is E, And this is like V, it's kind of like EV already if you just use, if you don't calculate the E. Okay, so yeah, there are some people prefer to just straight away put their E times the highlighted part, but never mind, you can just do your conversions as normal. So we're almost there. We got two EVs, but there's two answers with two EVs. There's a negative EV and a positive EV. So this negative positive is increase or decrease in kinetic energy. How do we know if it decrease or it increase? Let's ask the good old question. When you move from X to Y, is it getting faster or slower? Now bear in mind, this is the electron that's moving from X to Y. Normally, we'll say this is the higher potential, or say a positive. Here's a negative or lower potential. The electron does not want to go nearer to the negative plate, so it's going to slow down. So what's happening is, it's actually slowing down the more it goes towards the negative plate. So it's actually a decrease in energy. So here, really, you want to choose not the positive E, but the negative 2 EV, because it's a decrease in kinetic energy. Now, lastly, some of you will be like, Miss, I'm not satisfied. I want something more concrete. Okay. You want something more concrete. Here's your something more concrete. Charge of electron should be negative, so we should add negative here. Which means this should be negative, which means this should be negative. Some people prefer that way of dealing with negative positive sign. You can do that. Some people want to think of, is it getting faster? Is it getting slower? Are you rolling downhill and getting faster, or going uphill getting slower? Blah, blah, blah. You can use either way. Make sure you take time to wrestle through with these ideas until it makes sense. Others like, oh, okay, I can do already, memorize. Then come out another question, don't know how to do already. Okay, so make sure you know the basic concepts of these things. And this video is a little bit long, I know. Lots of ideas, potential, kinetic. But the bright side is there's not that much practice questions to do on the list. However, there's one structured question which I encourage you must try out. I'll create a bonus video explaining the walkthrough of that. The question list, very short question list, is down in the description below. Kind of like a reward for this extra long video. Okay, so go check it out. Try some practice questions, and I'll see you in the next video where we will look at the final bit of electrons flying everywhere in the electric field.